Hello, so this is the first Zoom meeting on the chapter 6 review. And one thing I will be using is this document called Solubility Rules and Polyatomic Ion document that you will find in the homepage of our Canvas course, under the chapter 6 module. And let me show the document now. So the document is showing you the list of common polyatomic ions, which you saw with chapter 5, actually. You may need that when you're told the names of the reactant and product, and before you can write the formulas, you may need that. Solubility rules will be used only in chapter 7. So you want to have this open, and the periodic table for chapter 6. So let's start with the review. So the review is starting with question, and they are not ordered by numbers. It's letters this time. The first question is A, list as many visual clues or other types of evidence as you can that a chemical reaction has occurred. So here, I'm not asking for examples, but more general clues, visual clues, or types of evidence, that tells you that a chemical reaction has occurred. And so there are many things visually that can tell you that a reaction has occurred. For example, a color change. And for example, when copper turns vert-gris, which is green, after a while, due to the weather, that's because it has turned into a copper sulfide. So a color change indicates a chemical reaction. Emission of light or a flame, for example, when you are burning methane or a gas or even wood, whenever you are burning something and it creates a flame, so it creates light. So you see emission of light, a flame, and so there is a emission of heat, right? You can feel the heat. So all of these are indication of a chemical reaction. Absorption of heat also will indicate a chemical reaction occurred. For example, when you are using those cold, you need usually to break an internal boundary between two reactants. And once the reactant react, they will absorb the energy from the outside, from the surrounding. And so it will feel very cold. So they are used as cold pack. Formation of a solid inside the solution. So for example, when you're mixing two aqueous solution, and they are clear to start with, and if you see a powder forming in there, that's the indication that you're forming a solid. The solid is the powder. Formation of bubbles. If you are, for example, dropping let's say aspirin or an anti-acid tablet in water, you see bubbles forming, right? And the tablet, slowly dissolves and disappear. And that's because it turns into a gas, carbon dioxide, for example, etc. So all these are visual clues that a chemical reaction has occurred, and they are all a good sign that a chemical reaction has occurred. So let's go to question B. Why is it necessary to balance chemical equations? So we do balance chemical equation to what we say to satisfy the law of conservation of mass. The law of conservation of mass says that matter cannot be created or destroyed, and it is conserved instead, right? Conservation of mass means you are conserving the mass, which means the mass you started, at the beginning of the reaction is the same as the mass you have at the end of a reaction. So to satisfy this law of conservation of mass that has been observed over and over. So, it's something that you have to satisfy because it's what you observe in nature. So what we do is we are balancing equation, and balancing equation means to make sure the atoms that were present in the reactant at the beginning of the reaction are still present in the product at the end of the reaction. So you're keeping the mass. If you're keeping all atoms of the same kind, if you keep the same number of each kind, you will keep the mass. So that's how, on the paper, we are making sure the mass is conserved. Question C. Can we change the number of atoms by changing the subscript of the reactant and product formula? So this is referring to, when you're balancing reactant and product. So reactant on the left side of the arrow, product on the right side. Can you change the subscript of the reactant formula or the product formula? Well, the answer is a big no. Do not do that. Do not ever do that. You are not allowed to change the formulas of the reactant or product, because that would mean you're changing the nature or the identity of your reactant and product. And so it's not the same reaction anymore. You're not talking about the same substances anymore. So this is a big no-no. Do not change the subscript of the formula. For example, in sapling, you may see that your cursor can go in between, inside the formula, and you could change the subscript, but do not do that. The numbers that we use to balance equations need to be put in front of the formula. And so we call them coefficient. These numbers are called coefficient, and we place them in front of formulas, and they apply to all the atoms that are inside that formula. So let's go now to question D. And question D is, practicing balancing. So write and balance the chemical equations that correspond to the following reactions. So in sapling, most of the balancing you will have to do, you're provided with the formulas of the reactant and product. But sometimes you may have to write from the text. Like here, all the examples I have, or almost all the examples I have here, are about, giving you the names of the reactant and telling you what they will produce and telling you the physical state. And then from there, you have to write the skeletal equation. What we call the skeletal equation is the first version of the equation before it is balanced. You need to understand what it means when we talk about the skeletal equation. So let's write the skeletal equation here for elemental boron. So that's why you need the periodic table. Boron is here. It's a metalloid, right? It's on that staircase line, zigzag line, and it's a metalloid, and it's a solid, right? So when you're told elemental boron, it means element as an element. It means boron as an element, and boron as an element will be a metal. So then you would start with B, and you would give it a physical state of S for solid. So S means solid. It reacts, so it's is produced. So you see, that means it's going to be after the arrow. So let me put the arrow first. It comes after the arrow because it says is produced in one industrial process by heating solid D-boron trioxide. Okay, so before, in the reactant side, we have D-boron trioxide. So just the fact that you have those or diboron trioxide, those prefixes tell you that it's a type 3 molecular compound, right? Made of nonmetals only, boron and oxygen. And so the prefixes tell you the number of each. So D-boron means boron 2, trioxide means oxide 3. Of course, these numbers are subscript, and it is important you write them as subscript, like this. right? And we've been told it's a solid. So you're heating this with magnesium metal. So we are adding magnesium metal on the reactant side. Okay, let's look at magnesium here. Magnesium is an alkaline earth metal from group 2A, and it's a metal, right? And whenever you have a metal, it means it's a solid at room temperature. Except, there is only one that is not a metal, and it's mercury. But all the others, all those elements below the staircase that are metals are, solids at room temperature as elements. So they will be represented with just their symbol and S for solid. And it means the solid metal. So we are producing elemental boron and then also producing a solid magnesium oxide as a byproduct. Okay, so magnesium oxide. Magnesium is a metal. Oxide refers to oxygen. Oxygen is a non-metal. So we are making an ionic compound made of magnesium and oxygen. And so let's think about the type of ions they make, because these are two predictable ions. And we can see here that magnesium being in group 2A will be a 2+, right? So 2+. Oxygen being in group 6A, you do 6 minus 8, 2 more steps to be like neon as far as the number of electrons goes. So that means it's going to be a 2-. It likes to gain 2 electrons. So Mg2+ and O-, you see that the charges cancel, and so you need only one of each. So that means it's going to be MgO, and you're told it's a solid. So MgO is magnesium oxide. Okay, so this is what we call a skeletal equation here, right here, okay? It's not balanced, that's what it means. It's telling you only the formulas of the reactant and the product, and it's not balanced yet. So now let's balance it. So the way to balance is that you start by counting the number of atoms of each kind on both sides of the arrow. So you start with boron. So on the left side, we have 2 borons from that subscript here. On the right side, we have 1 boron, the elemental boron. Oxygen, we have 3 oxygens on the left side from B2O3. And then 1 oxygen on the right side in MgO. And finally, magnesium. We have 1 magnesium here, the elemental magnesium on the left side. And then on the right side, we have also 1 magnesium in MgO. So you're counting how many atoms of each kind you have on both sides of the arrow. And you see where they are not equal. And here we have 2 boron on the left and only 1 on the right. So we want to balance boron here. To balance boron, you need to make it, times 2 on the right side. Because if you do that, you will balance boron, right? Because you have 2 on the left, so you want to make it 2 on the right. And that times 2 that you need to do is the coefficient that you will place in front of boron. So here, let's place the coefficient of 2 for boron so that we balance the boron. That changes only boron because it's by itself here. Now, oxygen, we have 3 on the left, only 1 on the right. So let's make it 3 on the right as well. And let's give it another color here. So we want to multiply the number of oxygen by 3 on the right. And so the coefficient of 3 here will have to go in front of the formula that has the magnesium, and that's in front of MgO. However, when you're doing that, the 3 applies to the whole formula, MgO. So you're making oxygen 3 times on the right. So that's going to be equal to the 3 oxygen on the left. However, it changes also the number of magnesium. So this coefficient also applies to magnesium. So that means you have 3 magnesium on the right now and only 1 on the left. That's easy to balance because magnesium is by itself on the left, and that's the best you can hope for, because whatever you put in front will only change that element. So let's place times 3 here and put a coefficient of 3 in front of magnesium solid on the left. And so this should balance it. So let's verify. 2 boron on the left, 2 boron on the right. 3 oxygen on the left, 3 oxygen on the right, 3 magnesium on the left, 3 magnesium on the right. So this is balanced. So now the skeletal equation is balanced. So we can call it a balanced equation. So that's how you do it. Let's go through a second example. So we have sodium sulfide solution reacts with magnesium iodide solution to produce solutions of sodium iodide and magnesium sulfide. So we have this word everywhere, solution, right? Solution, solution. Solution means an homogeneous mixture, and usually when nothing is specified about the solvent, it's an aqueous solution. And so the physical state in this case will be AQ for aqueous, right? So we are using AQ for aqueous. Aqueous comes from aqua, which means water in Latin. And so an aqueous solutions is a solution made of a substance dissolved in water. So this is important to recognize that whenever we talk about a solution, when the solvent is not specified, it refers to an aqueous solution, so made of water, and then the substance is dissolved in it. So here, sodium sulfide solution means you have sodium sulfide dissolved in water. And so the physical state will be AQ for this one. So let's write the skeletal equation. And here we have sodium sulfide reacting. So that's in the reactant side. So sodium is Na, right? Let's find it. Sodium, just right there. And sulfide means the sulfur here. So these are, again, predictable ions. And sodium being in group 1A is going to be a +1. And then sulfur being in group 6A is going to be a -2 ion, just like oxygen, because it needs 2 more electrons to be like argon. So we have Na plus and S2 minus. So it's Na plus, and then it combines with S2 minus. So these are ions formula. So for the ions, the charge is written in superscript, right? It's very different from the subscript that we had earlier. So these are the ions. So let's find the formula of Na and S2 minus. So here you can do the crisscross trick, and you can see that the 2 of the charge of the sulfide will become a subscript for sodium. So it's going to be sodium 2, and sodium is not a subscript here, only, oh, it was superscript. So here, sorry, this is a subscript for sodium, and that comes from the 2 of sulfide. And then we have S, and S will get a subscript of 1 from the sodium, so just S. No need to write the 1, it's implied. And we said it's a solution, which means you need to write that it's aqueous for the physical state. Okay, it reacts with magnesium iodide solution. So another solution which is made of magnesium. So we saw earlier magnesium is a 2+ ion. right? From group 2A, so 2 plus ion. Iodide, so let's look for iodine. Iodine is in group 7A, it's an halogen. And as all halogens, it's making a -1 ion. So it's I minus. I minus. So the I is written normally, and then the -1 is a superscript. So again, we can use the crisscross trick to find the formula. And you can see that the 2 of the 2 plus from magnesium can become a subscript for iodine. So that's going to be a subscript here of 2 for iodine. And the one from the iodine charge will become a subscript for magnesium. So it's just magnesium and then I2. Again, that's an aqueous solution. So AQ here. And it's true, it's better as a subscript like that. Okay, so that gives you the formula of the 2 reactants. Now we need to write the arrow and find the solutions of sodium iodide. So now we have sodium combining with iodine. So let's put them together here. So sodium with iodine. You can see that, you know, they each have one charge, one positive, one negative. So one of each ion will make this a neutral formula. So that's going to be the formula for sodium iodide, and then magnesium sulfide. So it's going to be magnesium with sulfur. You can see the 2 plus from the magnesium will cancel the 2 minus from the sulfur. So again, one of each ion is enough to make this a neutral formula. So it's MgS. So we have now the formulas for our reactant and product. And as it is now, we call this a skeletal equation. It's not balanced yet. So let's do the counting of each type of atom. So we have sodium on the left. We have 2 from here, 2 sodium. And on the right of the arrow, we have 1 sodium in NaI. S, we have 1 on the left, 1 S on the left, 1 sulfur. On the right, we have 1 sulfur as well. Oops. Hola. Talk here. 1 S. Magnesium. We have 1 magnesium on the left in MgI2, and then 1 magnesium on the right. Iodine. We have 2 iodine on the left in the MgI2. And on the right, we have only 1 iodine in NaI. So that counts the number of atoms of each kind on both sides of the equation, of the arrow. So let's balance. It's always a good idea to balance metals first when you have metals and non-metals. So we have 2 sodium on the left, only 1 on the right. So let's make it 2 on the right so that we have the same number on both sides. So the coefficient of 2 will go in front of NaI because that's the formula that has the sodium. However, when you're doing that, it also changes the number of iodine. So the times 2 here also will change the count of iodine to 2, which is convenient because we had 2 iodine on the left and only 1 on the right, and now we have 2 on the right. So it balances the iodine. Is it enough? Do we have to? Looks like we have 1 sulfur, 1 sulfur, 1 magnesium, 1 magnesium, you know, 2 Na, 2 Na, and 2 I and 2I. So that's it. It balances your equation already. So sometimes balancing is very easy like this. So question 3, many over-the-counter anti-acid tablets are now formulated using calcium carbonate as the active ingredient, which enables such tablets to also be used as dietary calcium supplements. Calcium carbonate reacts by combining with hydrochloric acid found in the stomach, producing a solution of calcium chloride, converting the stomach acid to water and releasing carbon dioxide gas. So the first sentence here is just for your information. So it's an anti-acid tablet, which means it it's to relieve acidity that people experience, heartburn because of the acidity going up the esophagus. And so calcium carbonate has the advantage of, at the same time being used as a dietary calcium supplement. But the equation, you can write it only using the second equation, so sentence, I mean. So we have calcium carbonate reacting, and so that's going to be on the reactant side. So calcium carbonate, let's find calcium in the periodic table. Calcium is in group 2A, it's an alkaline earth metal. So it's a predictable ion with 2 positive charges. So 2 plus. And here that's superscript. And then carbonate. Okay, carbonate is not in the periodic table. And that's where the document I showed you at the beginning comes handy. Here, carbonate, because it ends in 8, it's indicating that it's a polyatomic ion, because a lot of polyatomic ion ends in 8, like sulfate, phosphate, nitrate, acetate. So let's find carbonate here. And if you see it in the right side, right column, it's the first on top of the right side, carbonate, CO3 negative 2. So you want to use this list to help you find the correct formulas for your polyatomic ion. So let's write this then. CO3 with 2 negative charges. So the 3 is a subscript and the 2 negative charges are a superscript, right? Please be very careful how to write this. The 3 is a superscript for oxygen. It means you have 3 oxygens surrounding the carbon. And then the 2 negative charges is for the whole thing. It's negatively charged with 2 negative charges. So let's find the formula from these 2 ions. And you can see that the 2 positive charges will cancel the 2 negative charges. So it's just a matter of putting one of each ion. And so the charge cancels out. And here, this is tablets. So that's a solid. The tablets are solids. Next, you add, because it reacts by combining with hydrochloric acid. So you did not learn how to name hydrochloric acid in chapter 5, even though it's in the chapter, of course, in the textbook. But I kept it for chapter 7 when we go over chemical reactions. And so hydrochloric acid is the way you name an acid that is a monoatomic acid, if you will. The hydro in front tells you it's only a chloride, or the chloride ion. And acid means you will have H as first in the formula and then just Cl. Because the chloride ion is Cl minus 1, right? It's an halogen from group 7A. So it's a -1 ion. And H, when it's an ion, it's a +1. So together, when you place them together, it's the hydrochloric acid, HCl. We always write the formula of acids with the H first in the formula. That's how we recognize acids. Another thing about acids is that they are always aqueous. If you call them an acid, then it's aqueous. If it was not dissolved, because this HCl by itself is a gas, but when it is an acid, it's when it's dissolved in water. So here it's dissolved in water. And let's write this. Okay. So they react together, and let's put down the arrow. By producing a solution of calcium chloride. So it's a solution, so it's going to be aqueous. Calcium chloride. Oh, I guess I could have had the H plus here and the Cl minus. So we have calcium chloride. So the calcium ion is Ca2 plus. The chloride ion is Cl minus. So here, if you do the crisscross trick, you see that the one charge of chloride will make a subscript of 1 for calcium, which we omit and don't write. And then the two, from the two positive charges of calcium becomes a subscript of 2 for chlorine, right? And you are told it's a solution, which means it's aqueous. So that's one of the products. The other product is water. Solution of calcium chloride converting the stomach acid to water and releasing carbon dioxide. So you're producing water. You should know that it's H2O. And that's liquid, okay? Water is always liquid, solid, or gas, but it cannot be aqueous, right? It's the solvent. So don't make it aqueous, please. And then carbon dioxide gas. Carbon dioxide is, you see that prefix di tells you it's a molecular compound or covalent compound. And the di tells you there is 2 oxygen for 1 carbon. And that's a gas. Oops, gas. So G is for gas. And we can have all of this like this, okay? So symbol L for liquid and symbol G for gas. Aqueous for AQ for solutions. And then S for solid. So this is the skeletal equation. So let's now make a count of each type of atom on both sides of the equation. So on the left, we have 1 calcium from calcium carbonate. And on the right, we have also 1 calcium in CaCl2. Carbon. So CaCO3 is a polyatomic ion, and you will later on learn that when you have a polyatomic ion, and if it stays the same from left to right of the arrow, then you want to count them as a whole. You don't want to dissociate the carbonate, the oxygen from the carbon. However, here we do not keep the carbonate. The carbonate becomes, carbon dioxide here, which is not the same formula exactly. So, and one of the oxygen goes to water. So because of that, we will dissociate the carbonate into its elements. But you will learn also later on that whenever you have a polyatomic ion that stays as the polyatomic ion from left to right, then you want to count the polyatomic ion instead to save time. It's a lot easier to do that. So here you would take 1 carbon and then find how many carbons on the right. There is 1 carbon also from the carbon dioxide. Oxygen, we have 3 oxygen on the left from the carbonate, and then oxygen on the right. So we have 2 oxygen in the carbon dioxide plus 1 here. So that's also 3 oxygen on the right. Hydrogen, we have 1 on the left in the HCl. Oops. And then 2 hydrogens in the water there. So 2H on the right. Oh, we are missing the Cl. So 1 Cl on the left in the HCl. And then 2 Cl on the right in the CaCl2. So 2 Cl there. There we have all our elements. So we can see the calcium are balanced, so we cannot balance that first. Carbons are balanced as well, oxygens are balanced. The hydrogens are not balanced. So let's balance the hydrogen. So we have 2 hydrogens on the right. So let's make it 2 hydrogens on the left. So by multiplying by 2 here on the left. So this coefficient of 2 will have to go in front of the HCl because that's the molecule that has the hydrogen. So let's put a 2 in front of HCl to balance the hydrogen. However, the 2 in front of HCl also applies to Cl. So that means the times 2 you have put there will also change the count of chlorine on the left side to 2. And it happens we have 2 chlorine on the right side already. So that balances the chlorine at the same time. So let's see, is it balanced otherwise? So 1 calcium on the left, 1 calcium on the right. 1 carbon on the left, 1 carbon on the right. 3 oxygens on the left, 2 plus 1, 3 oxygen on the right. 2 hydrogens on the left, 2 hydrogens on the right. 2 chlorine on the left and 2 chlorine on the right. So this is balanced. Again, that's an easy equation to balance here.